Welcome to Physics 163, Chapter 16, Part 2, Lecture number 6, Continuous Uniform Charge Distributions. We're going to do the disk, the hollow sphere, the solid sphere, and also show you what a capacitor is. So today, hopefully by the end of this podcast, you will review the ring charge. You will explain the uniform disk of charge, explain two disks of charge or the capacitor, explain uniform hollow spheres of charge, and explain uniform solid spheres of charge. And by the end of today, I hope you have a better understanding of these continuous charge distributions, particularly the capacitor model. Alright, so let's review all the types of electric fields we've talked about so far. We've talked about a point charge. We've talked about the electric field outside a uniform charge sphere, which is just like a point charge. We've talked about it inside the uniformly charged sphere, which is zero. As a matter of fact, I'll show you today why it's equal to a point charge and why it's zero inside. We've also talked about dipoles. We've had two types, one that's on the axis with the dipole and one that's perpendicular to the axis of the dipole. We have talked about a uniform line of charge, and if L, which is the length of charge, is very long compared to the distance you're away from that charge, then we can approximate the electric field as 1 over 4 pi epsilon naught Q divided by L divided by R. Else, if that approximation fails, then what we do is we have to use the other representation if L and R are equivalent distances. And then I believe we've talked about the ring of charge, where the ring of charge is equivalent to this. So what we're going to do today is use these ideas, or at least the ring of charge. We're going to want to review that again. And if we look at this animation, remember we're breaking up the ring into individual charges. The green is the distance the charge is away from our observation point. The magenta is the electric field created by that individual element, and the gold is the total electric field. And you can see it all adds up and points directly away since the charge is positive. If the charge was negative, it would point towards the ring. So using that idea, what we're going to do is talk about a disk. And for a disk, we're going to model it as a whole bunch of rings. And so you can see here, if we're a distance above the disk, that the electric field points away from the disk if the disk has a positive charge. It would point towards the disk if the disk had a negative charge. And you can see that the electric field gets quite large. And no matter how it's oriented, it always points away from the disk since the disk has positive charge on it. You can see even when it's oriented in a different direction, it still points away. And we're going to assume we're over the center of the disk. Alright, so how do we actually calculate that electric field? Well, we're going to represent our charge, or calculate this electric field in a similar manner we've done in the past. We're going to calculate the infinitesimal element of dE created by every ring of charge in the disk. And so to do that, I have to take out my formula for the electric field for a ring of charge, and then I've changed my Q here. It's now dQ, and that is the Q or the charge stored on this ring. So what we're going to do now is figure out what that dq is. By definition, since the total disk has a charge q on it, I am going to multiply that charge q by the area of the ring divided by our total area. And the reason we're using area is it's a two-dimensional object. That's why we're going to use area. So what is our dq? Well, our area of the ring is the circumference of the ring times its thickness. So that's going to be 2 pi r times delta r. And the whole area of the disk is pi times r squared. Now, if we simplify that a little bit, we get this relationship. And that's my dq. So I'm going to make these infinitesimally small so we can do our integral. And so I'm going to put my dq back into my equation for the electric field. And in this case, since the electric field only points in the z direction, I'm only going to do the zth component of that because we don't have a component in the x or the y direction. So let's simplify that. Okay, so now I want to find the whole electric field. To do that, I have to integrate this over all the rings that exist in my disk. So I'm going to factor out whatever's constant. The 2q over r squared and z are all constant. And remember, z is the distance we're above the disk, or away from the disk according to the picture we see here. And I'm left with this integral here. So now what we're going to do is now what we're going to do is figure out our limits. Well, the radiuses of our little rings change from 0 all the way out to the total radius of the disk. So from 0 to capital R. And we need to integrate that. And to integrate that, what do we have to do? Well, we're going to have to do a substitution. What substitution do we want to use? I'm going to use this substitution. I'm going to set u equal to r squared plus z squared. And then now if I take the derivative of that, I get du is equal to 2r times dr. Remember, z is a constant in this integral. And then this allows me to replace r dr with u du. And if I plug that into my integral, I have to integrate this. Let's factor out some constants. And so what we're going to have is we have to do this integral. And that integral is fairly easy. I'm going to rewrite it this way. And if we do that, it's just a power law. What I need to do now is plug u back in. It turns out to be this. Well, u is defined as r squared plus z squared. And then evaluate it at its limits. Let's evaluate it at its limits. We get this. And let's do some simplification. So I got rid of the exponents and just write it out normally how we would see it with the square roots. And since this is z squared, take the square root of it, it's just z. Let's multiply through by our minus 1z. And if I do that, we get this expression. And I also simplified my coefficients here. I brought the r squared down the bottom, and so I got a pi r squared, which is going to end up being the area of the disk, and that's equal to multiplied times this constant, so 1 over 2 epsilon naught. So this allows us to calculate the electric field for any disk of radius r that is uniformly charged across that disk, and some height z above that disk. So let's look at some approximations to this model. And what we're going to do here is, normally it's written this way. So let's say that we're in a region where z is greater than 0, but the radius of the disk is much, much greater than the height we're above the disk. If that's true, then I can approximate my electric field this way. So R is big compared to z, so we can ignore this small number, and because this is going to dominate, and take the square root, we're just left with R. So I'm left with this expression. Now, if R is big compared to z, and that makes z divided by R small compared to 1, I can make an additional approximation. And that is that this z divided by R is so small it's almost 0. I can approximate the electric field above a disk, if I'm really close to the surface of the disk compared to its radius, as being a constant value, or Q divided by its area of the disk divided by 2 epsilon naught. This is going to be an important relationship when we want to define this capacitor model, or two uniform disks together. So here's a problem. We have two uniform disks, one positively charged, one negatively charged, and the electric field inside is E. They want to know what the electric field is out here at this X. So which arrow best represents the electric field at X? So what I want you to do is pause the podcast and come up with an answer, or what answer you think. And then I'll help talk you through why I think what the answer should be. Alright, so what is the answer to this question? Well, let's look at how the electric field is created. So there's two charge distributions here. You've got a positive one and a negative one. So how does the electric field look coming off a positive disk? Now if you look at this picture here and here, this looks like they want this to continue out. It says a large capacitor. So these radiuses here are going to be large compared to any of these distances. So if we do that, what's going to happen? Well, I get my electric field caused by my positive charge should point that way here. I get electric field from my minus charge because electric field points towards minus charge. And so I get this net electric field inside because these two will add up to be that one. Well, let's do the same strategy over here at point X. Which way should the electric field caused by the positive charge be pointing? Should have said negative charge. I apologize. Which way should it be? The negative charge should be pointing towards it, but the positive charge should be pointing to way the positive one. You see how these are different? Now, what we're going to make an assumption here is that this distance here and this distance here are still small compared to how big the radiuses are. And if we do that, remember, our electric fields were constant, if that's true. They should cancel if the size of minus q and the amount of plus q are equal in magnitude, not in sign. So this should be 0. So the correct answer here should be 3. The electric field should be 0. Now even if we look over here, what should it be? Well, the electric field from the positive charge should point away. The electric field from the minus charge should point which way? That's right, it should point towards it. So again, they add up. And if we make the assumption again that the distance between here and here and there are small compared to the distance, the radiuses of the disk, then this electric field should add up to be, the net electric field should add up to be 0. Well, the book also, when we talk about these two charge disks, the book also talks about that this electric field out here might not be 0 if our disks are not large enough. That is 100% true. And it's called a fringe field. Now, I think the book does an excellent way of showing you what that fringe field should be. And I'm just going to let you read it in the book because I think it does a very good job of explaining it. So what we'll do now is move on to a question. So here, you stand at location A, a distance d from the origin, and hold a charged ball. You find that the electric force on the ball is 0.008 newtons. You move to location B, which is a distance 2d from the origin, and the electric force on the ball is 0.004 newtons. What object located at the origin might be the source of this electric field? So I want you to determine an answer from these 8, and then pause the podcast, pick an answer, and then I'll help you talk through the correct answer. I'll help you talk through how to get to the answer here in a little bit. Well, in my opinion, the correct answer is a uniformly charged rod. Well, why is a rod? Well, if we look at the force here, the force initially is 0.008 and it's 0.004 accurate, so it's divided by half. It's half, so it has to, somehow, we have to figure out how to reduce it by half. To do that, we know that the electric force on any charge is equal to its charge times its E field. So we have the same charge in both spots, so this doesn't change, E has to change. E has to reduce by half by increasing its distance by 2d. Now the only electric field we know that will reduce by half if we double the distance between them is what? A uniform line charge. It's if L is large compared to how far we're away R. It's related to 1 over R here. Well, we go from 1 over D to 1 over 2D, or 1/2 of what we originally had before. And that reduces the force by 1/2. So it has to be a line charge, or a uniformly charged rod at the origin. So here's question 3. You stand at location A, a distance d from the origin, and you hold a small charged ball. You find that the electric force on this ball is 0.08 newtons. You move to a location, a distance 2d from the origin, and find that the electric force on the ball to be 0.01 newtons. What object located at the origin might be the source of this electric field? So I want you to pick an answer from these 8 choices again. Pause the podcast. Determine what answer you think is correct. Come back after you've determined the answer and see if we can talk through why your answer is, why you should choose this answer. So, I think the answer is number 2, a dipole. Why should it be a dipole? Well, if you look at the force, if we look at our relationship between electric force and electric field, the charge does not change again, but the force reduces by 1/8 of its original value. So the electric field has to reduce by 1/8 if we increase the distance to 2d. So which electric field would allow us to do that? That's the dipole field. The dipole field is proportional to 1 over r cubed. So if I put 2d in r, the 2 is going to get cubed. That would give us 8. That will reduce the electric field by 1/8. Alright, here's another question. Again, you're standing at location A. You feel a force of 0.009 newtons on your charged ball. You move to a distance 2d from the origin, and you find the electric force on the ball is 0.00899 newtons. What object located at the origin might be the source of the field. Again, you've got to choose from these 8 answers. Again, pause the podcast, determine your answer, and then we'll come back and talk about how to find the answer. I believe the answer is a uniformly charged disk. It's either that, or we're inside a capacitor. But I don't see how we could be inside the capacitor, because we go from a distance d to a distance 2d from the origin. I still think it's a better choice as a disk. Why? Again, electric force is the relationship of your small charge on the ball times its electric field. If you move from one location to the other, the force does not change much. It's almost approximately the same thing. So the only electric field that we have that is exactly the same is that of a uniformly charged disk, if d is small compared to the radius of the disk. And that's the only one that would match. All the rest would change if you move farther away. Alright, let's talk about how we can generate a uniformly charged hollow sphere with the information that we have so far. And the way we do that is I'm going to use rings. And so I'm going to generate my charged sphere by using rings. Here the green arrow is the electric field caused by the ring itself, one ring, the new ring, and the gold is the total electric field for all the rings. And as you see, as we create this, that the electric field points away since the charge is positive. But if you were far enough away, you would think this sphere this sphere could be a point charge. It looks exactly like the electric field from a point charge. And no matter where we point it, it always points away because the charge is positive. If the charge was negative, it would point towards it. So we can generate our solution for a uniformly charged hollow sphere by using a set of rings of different radiuses at different positions to create the surface of the sphere. Well, this allows us to get the outside, but we already knew what that was. That's the same as a point charge. So I'm going to show you the correct answer now. The answer of why the electric field inside a uniformly charged shell or sphere has to be 0. Now if you look at this, the gold is the total or net electric field, the green is the electric field caused by each new ring, and you can see that it is getting very small and has changed its direction as it passes the observation point. And you can see that the net electric field is getting smaller as we keep adding more and more rings. So if we keep adding more and more rings, what do you think might happen to our electric field at this point? And as you can see now, the green arrow is practically non-existent. Or I should say the gold arrow is practically non-existent. It doesn't exist. If you look in there, it is almost gone. It's fat. It's basically as small as the computer will allow it to get. And that is why the electric field inside a uniformly charged hollow sphere is always 0. Alright, so I have another question for you. The electric field at a location inside a hollow uniformly charged sphere due to the charge on the surface of the sphere is 0. Because of what? Look at each of the answers. It's true or false. Which answer is correct? 1. If 0 is true because the electric field cannot penetrate the material of the sphere. 2. True because the contributions of all the charges on the surface add up to 0 at every location inside the sphere. True. Number 3, true, but only at the center of the sphere where all the contributions cancel. 4, false, because the electric field due to the surface charges penetrate the sphere. So again, pause the podcast, determine your answer, and then come back later and we'll walk you through how you can determine what the correct answer, or what the answer, define what the answer should be. I believe the correct answer is 2. Well, because I just showed you the video, the animation or the simulation of why that happens, is because the electric fields from all the charges on the surface add up to be a net field of 0 inside. I can tell you why 1 is false, because electric fields penetrate all matter and all materials. So 1 is false. 3 is false. It happens at all places in the sphere. And 4 is not correct, because the electric field of a surface charge does penetrate the sphere, so it has to add up to 0. Alright, let's practice these new ideas that we've learned. Okay, so we have a spherical shell. A uniformly charged sphere is shown. What is the direction of the electric field at location A? Again, pause the podcast, choose your answer, and we'll talk through why it's true, or how to get your answer. Alright, if you've been paying attention to the last couple slides, you should have chosen the correct answer. At least I hope you should. The correct answer is 9. It's 0 magnitude because it's a uniformly charged shell. All the electric fields caused by all the charges on the surface cancel out while they're inside. So the electric field at A has to be 0. Now I have 2 concentric shells are uniformly charged as shown. What is the direction of the electric field at A? Again, pause the podcast, and then when you've chosen an answer, you can come back and we'll talk about how to step you through to find the answer. Alright, to me the correct answer is 2. It should be pointing in that direction. The question is why? Well, let's talk about it. Let's find out here. So we're here at location A. I'm inside one sphere and I'm outside the other. So the electric field caused by the charges on the outside here would produce what electric field at A? They have to be 0 because it's uniformly charged on the outside. So that charges on the outside sphere will not affect the electric field on the inside. And then we have the inner sphere. You will get an electric field from the inner sphere. A is outside its radius. It's not inside the smaller one. And it points directly away from the sphere. And the best direction is 2. That's why 2 is the correct answer. Let's try this one. I have a spherical plastic shell. It's plastic, it's dielectric. Its charge is shown. What is the direction of the electric field at location A? Pause the podcast, choose an answer, and then come back and we'll talk about how to find the answer to this question. Okay, the correct answer here is 3. Why is it 3? Well, if we look at A, this is not uniformly charged. It is a sphere. It's not uniform, and it's plastic. It's a dielectric. So if you're at A, the biggest component of electric field you're going to see is caused by this minus charge, and so it should point towards it. And then there should be some by this, but these are all symmetrical. That's symmetrical. That's symmetrical. I think the net electric field should be pointing in direction 3. Because this plus charge will be pointing that way, this one would be pointing that way, they would add up to point this way. Same thing about the negative one there. This one's pointing that way, this one's pointing that way. They're going to add up to 0. I think the biggest ones are going to be this way. It'd be a net field pointing in direction 3. Alright, let's try this one. Now we have a solid metal sphere is charged and polarized as shown. What is the direction of the net electric field at location A? Again, pause the podcast, determine your answer, and then after you've got an answer, come back to the podcast and we'll step you through the procedure of finding out what the answer is. I think the correct answer is 9. Why? Well, it's a solid metal sphere. Metal is a conductor. So the net electric field inside any conductor, if it's in equilibrium, has to be 0. Because whatever external electric field polarized it, it's going to be canceled by the electric field created by the polarized charges. And so the net field inside will add up to be 0. Alright, so we haven't talked about a solid sphere with a uniform charge spread out over its entire volume. Usually this sphere has to be a dielectric because the conductor won't hold charge internally. They would be able to move around and put the charge all on the outside. So we're going to talk about, when we talk about it, it's going to have to be plastic. So what do we know about a uniformly charged sphere? Okay, we know it has an electric field, and that electric field, if you're outside it, is equal to the electric field of a point charge, where Q is the total amount of charge stored in its entire volume. So the big question is how do you find it inside? So here we have the red volume. I'm at a spot right here, and I want to know the electric field inside this charged object. Well, how do we do that? Well, what do we know about electric fields of charged shells? So what we're going to do is divide our total volume into concentric shells of all different radiuses, but all these shells have the same thickness dr. That means the electric field caused by all the charge outside the point I'm looking at does not matter because I'm inside a uniformly charged sphere of this blue. So that charge does not affect the electric field that I see. The only charge that will affect my electric field that I see is the charge that's inside the red here, the small one. So what we're going to do is calculate our electric field. Well, that's a charged cylinder. I know how to calculate the electric field for a charged sphere, not a charged cylinder. I know how to calculate the electric field for a charged cylinder. It's like a point charge. But how do I determine the amount of charge in my sphere, this dq I've got there? Well, dq is going to be defined as this. I take the total charge on my sphere. I multiply it by the volume enclosed in the interior, or this small red area volume, and then divide that whole by the total volume of the sphere. So I'm going to do that here. We're going to make our this radius r, that's our internal volume, so it's 4/3 pi r little r cubed, and our outer volume is, we'll say it's a big R, so it's 4/3 pi r cubed. And you notice we have a lot of things canceling here, and I get this relationship for dq, delta q. Well, I'm just going to plug that right back in. And if I do that and I simplify this expression, I get this. What we find out here is Q and big capital R are all constants, and the electric field is proportional to R. It's linearly proportional to the radius you're away from the center of this sphere, and this allows us to calculate the electric field of a solid sphere where there's uniform charge spread throughout the sphere. And so now you know how to do that. Alright, so this brings to end the podcast on Chapter 16 of Continuous Charge Distribution. I hope you have a better understanding of a uniform disk of charge, and then how, depending on how close we are to the disk, we can get a constant electric field. And then I hope you have a better understanding for how to figure out the electric fields for two charged disks placed closely together, what we call the capacitor. And remember, if you're outside the capacitor, if you're not between the two plates, you get an electric field there between the plates. But if you're outside the capacitor, you don't have an electric field out there. That's usually the ideal capacitor that happens that way. And then you should understand how we use concentric rings of different radiuses to calculate the uniform electric field for a hollow sphere of charge, and also how we use concentric spheres of charge to calculate a uniform solid sphere of charge. I'll see you guys on Tuesday. If you have any questions, you can send me. Thank you.